So, before we begin on the main part of the lecture, I just want to make one minor correction from yesterday's lecture. In the example where we talked about a rocket ship, I listed a condition which said that the position at time equals 5 was 10 million. And I originally wanted to say miles because that was what I had written down. But I wanted to keep everything in the metric system, so I switched it quickly to kilometers. But what I should have switched it to was meters to jive with the fact that we were given velocity in terms of meters per second. Okay, otherwise we have a little conversion problem. So we can switch that to meters. And then everybody feels better. Okay, so today we'll review a little bit about what we did yesterday. And then we'll start talking about classifying differential equations. Okay, that's where we're headed. So, yesterday we introduced differential equations, and the idea of the differential equation was simple. You have an equation, and it has derivatives in it, or maybe little differentials in it. Okay? And at the very end, or well, let's say first in the middle, we proved that if you had a function, right, and you could find a function whose derivative was your original function, right, and of course we called this new function an antiderivative, that there was really only one antiderivative up to constant, right, a plus c. Okay, so that was really nice. We were able to prove that. You just can't find two distinct antiderivatives. Right, that don't just differ by a constant. And then at the end, right, we've made the following definition. For any variable, x, we define this sign, which we call the integral sign. Right? We said that the integral of dx is some set, right, and the set is x plus c. Right? You look at all functions of the form x plus c, where c is a real number. And as I said later on, and by later on I mean very soon, we're just going to drop this whole set business and just call this x plus c. But I really want to emphasize, right, the integral is not just one function. Right? When you do the antiderivative, you're actually getting a whole set of functions, one for each real number. And then we said if f is a function of x, such that f is an antiderivative of, say, f of x, the antiderivative of little f of x, then, well, of course, that means that the derivative of big F is little f. That's just the definition. Furthermore, that means that the differential df, which is defined to be f prime times dx, is just little f times dx. And so this tells us that, well, if we want to make sense of this, the integral of a function times dx, that this should just be the same as the integral of df. And by definition, the integral of df is just f plus c, where c ranges through all real numbers. Yes?
Can you provide numericals?
That will be next. Yes. All right, so this tells us that the antiderivative, or the integral of little f times dx, is the set of all antiderivatives of little f. Okay, and remember, the set of all antiderivatives is given by just finding one antiderivative and then add all possible kinds. Very good. So now we have this nice definition. So as an example, let's compute the integral of x squared dx. So what we're looking for, by this, the integral of f dx, we need to write down a set, and we know what the set's going to look like. It's going look like something plus c, and c runs through all real numbers. The question is, what's the sum? Okay. Well, the something is an antiderivative for x squared. Any antiderivative. So we just need some function whose derivative is x squared. Okay, so what will be my function? 1/3 x to the third. That would work. If you were thinking about how do I get that, you might say, well, let's see. If the derivative is x squared, it should come from a polynomial with one higher degree, so it should come from an x cubed. But then when I take the derivative, that 3 will come down, but there's no 3 there, so it must have got canceled out by 1/3. Okay. Now, incidentally, this also would have been an acceptable answer. Right? What's the derivative of 1/3 x cubed plus 1?
X squared.
Still x squared, right? All this says is you find any antiderivative, and then you can add a constant. Of course, these steps are the same. As c runs through all real numbers, so does c plus 1. Right? I can get any real number of the form 1 plus c. Let's try it. Give me any real number. 36. Okay. I can write 36 as 1 plus 35. Okay, so every real number is in this too. Okay. I'm just pulling out constants. I can play with these things all I want to, right? Okay, let's do another one. Let's do the integral of sine of x times dx. Okay. Now, right now I'm saying times dx because literally the way we wrote this down, you are multiplying these things. Okay, but later on, when we talk about it, we'll just say the integral of sine of x dx. We won't say times anymore. But for now, we'll be precise. Okay, again, we know that this is going to be something like that. Right? And what's the that? Well, the that is an antiderivative. So we need a function whose derivative is sine. Negative cosine will work, yeah? Okay, so I put negative cosine of x plus c. And of course, just as before, I throw in a 2 pi in there. Right? Cosines and 2 pi's, they seem to live near each other. It seems reasonable, right? These are the same answer, right? Well, what's the derivative of minus cosine of x plus 2 pi?
Sine.
Sine of x, same thing, right? And why? Well, this 2 pi is just another constant. You add two constants together, you get another constant. Okay, you're not messing anything up. Okay. So that's why, and because and the important thing, right, is we're taking the set of them over all real numbers here. If we only looked at, say, positive real numbers, right, then these sets wouldn't be the same. Right? So if I started c at 0 and only went up, right, well then this one couldn't be plus minus 2. Okay? Now this one here, if I started c at 0, well the lowest you can get is 2 pi. Everything would be bigger than 2 pi. So it really would be different. But when you let c go over all real numbers, which is what we do, everything is cool. Okay, these sets are actually the same, even though they look different. Okay. Let's do a trickier example. Let's do, what do I want to say? Okay, let's recall just quickly. The absolute value of x is a piecewise defined function. It's defined greater than or equal to 0 and less than 0. And what is it when it's greater than or equal to 0? Just x, right? Just does nothing. And when it's less than 0? Negative x, right? Because if it's negative, the absolute value is supposed to make it positive. How do you make a negative number positive? Put a negative in front, right? Negative times a negative is a positive. So, well, got a negative, want to make it positive? Throw a negative in front. So already, this is kind of a strange question, right? An antiderivative, I want it to be one function, but in this case, it's going to be, in a sense, another piecewise defined function, right? It's really going to be composed of two different functions again. Okay? So let me define a new function. We'll call it f of x. And it's going to be the antiderivative of absolute value of x. And we're just going to define it again on these two ranges. Okay? So when x is, you were all thinking it, but nobody said it. Thank you. When x is greater than or equal to 0, then the function is just x. So what will be an antiderivative for x? X squared over 2, right? Or 1/2 x squared. And what about minus x?
Minus 1/2 x squared?
You got it. Minus 1/2 x squared. And if you want to test that, just take the derivative. 2 times 1/2 is 1. The minus stays there, you get minus x. Okay, cool. Okay. So this is actually, well, I don't want to rewrite this all within the set, so I'll just write f. Let's see. Okay, where this is f. Any questions on this? Yeah.
I'm sort of confused, like, I understand how you integrate it, but like when you go from like, what is like big F of x and what's small f of x?
Okay, so in calculus, we normally start, we don't call it that normally, but start with big F. I might have, say 3x. And then I take the derivative. The derivative, say, would be 3. This is what I'm calling little f. One way to think about it is when you have polynomials, right? If I take x cubed, okay, what will little f be? 3x squared. What's happening to the degree? It's getting smaller. Yeah, it's going down by 1. Okay, so for polynomials, you're getting smaller. So I go from big F to little f. The f is getting smaller. Okay, that's how I think about this. Okay, of course, it doesn't make any sense for sine of x, this becomes cosine of x, but in no meaningful way is this smaller than that. Okay, but for polynomials, f is smaller. Okay, now, in the real world problems, you find an antiderivative, okay, which means you get this f, and then the integral is, right, all of these possible antiderivatives, so f plus c. So you have this whole set of all these possible solutions. Fine, but in the real world, there aren't usually infinitely many solutions. Okay, there's usually maybe 1 or 2 that could possibly work. So what do you do? Well, that's when we have this other initial data. For instance, in the rocket ship problem, it was the S of 5 is 10 million. Right? Or in this, we had another problem, n of t. We had n of 0 is 60. Okay? And that helps you choose the correct function from this infinite set. Okay, very good. Okay, it's a very nice problem. You have real world phenomena. You model it with a differential equation. You solve the differential equation, and now you understand that real world phenomenon. Cool. How do you do it? How do you do that last part? Right? How do you actually solve these things? Well, there's way too many of them for us to know how to solve all of them and have tools for all of them. But of course, you do your best. You try to solve problems anyway. And the first step in trying to solve a massive problem like this is to break down the problem into manageable chunks. You try to see, okay, how can I classify this in such a way that at least I can handle at least certain families of problems. So for instance, in algebra, you look at linear equations, right? Things of the form ax plus b. Okay, these are very nice. They're very well behaved. You You can learn all sorts of cute little formulas about it. Right? Very useful. Okay? And then you go a little bit further and they say, oh, well, you know, this doesn't really model everything in the real world. For instance, throwing a ball up in the air doesn't satisfy a line. So they say, let's talk about quadratics. Okay? Second degree polynomials. They give you a little extra. And you go a little further out, right? You might look at cubic polynomials. So when you try to model things in the real world with polynomials, you see that, right? One way of breaking up that study is by looking at what is the degree of the polynomial that you have to use to model it. So in this case, right, you're looking at, you might think first degree problems, and second degree problems, and third degree problems. So we're going to do a very similar thing with differential equations. We're going to try to classify them in some natural way. So the first one is going to be called the order of a differential equation. This is very easy. The order, and I'm usually going to abbreviate differential equation because it takes a lot of space. The order of a differential equation is the highest derivative in the equation. So for example, here's a nice second order differential equation. Okay, why is it second order? Because the highest derivative is the second derivative. Notation, you may recall, if I want to write the derivative of a function, I can either use this Leibniz notation or this alternative notation where I write the function to a power, but I put parentheses around the power. That says don't take the third power, that means take the third derivative. And so the parentheses always tell me that. So assume I have some function y of t, and I take the third derivative of y minus y equals 2t. What's the order of that derivative? Or that differential equation is third order, right? Okay, so this is the second order, this is the third order differential equation. Okay, that's pretty easy, right? You just look, so it's the highest one. We're clever. Okay, so the motivation for looking at the order of a differential equation, you might think, well, the same thing as looking at the degree of a polynomial. Right? Very easy to spot, right? Of course, you might think the more derivatives you have, the higher the order, probably the harder it is going to be to solve. Well, it's not necessarily true, but it's not a bad intuition. Well, let me give you a different way. This is a less obvious way of classifying these things, but is a very useful way. Okay, so a differential equation is linear. Okay, so this is going to be counterintuitive. For me, when I hear linear, I think line. Right? That's well, at least you get out of algebra and algebra 2, and that's okay, linear line. Okay, fine. So it should be first order, right? Okay, wrong. Okay, linear means something completely different. Okay. So it's linear if it can be put in the form. All right, so we're going to assume here that I have a function y of t. And what I want is that it can be put in the following form. I have some other function of t times the nth derivative of y with respect to t, plus a function of t times the n minus first derivative of y with respect to t, plus, okay, you keep going down, decreasing derivative by 1, you get down to, say, the first derivative, dy dt, plus, well, now there should be a 0th derivative, and it should equal just a function of t. Okay, so this is, I know this is very weird looking. Okay, so let me give you some examples to differentiate between linear and, well, if it's not in this form, I mean, if you can't put it in this form, then it's not linear. What do you think we should call it? If it's not linear, you might call it
Non-linear?
nonlinear, right? So, otherwise, we call it nonlinear. Incidentally, in the popular literature, they like to throw this term nonlinear around. This word is something that's very complicated, something you can't solve. Anytime they want to tack on an adjective to something to make it sound like they're doing something impressive, like, oh, we're not just doing chaos here, we're doing nonlinear chaos here. Okay. It doesn't mean that things are necessarily all that much harder. There are linear differential equations that are very difficult to solve, and nonlinear differential equations that are very easy to solve. So it's not necessarily telling you which is harder. It's just it's a convenient way of breaking up the field. Okay, so let's give an example of linear. So let's say I have t times the second derivative of y plus 3 times the derivative of y minus cosine of t squared y equals 0. This would be a linear equation. Why is it linear? Well, we look, okay, so you have derivatives, right? And then, of course, you can think about this as being the 0th derivative of y, whatever. Okay, so you have these derivatives. Okay, but the important thing is when you multiply these derivatives by something, it's always just a function of t. Okay, 2t is a function of t. 3 is a function of t. It's a constant function. Cosine of t squared, nice function of t. 0, very nice function of t. This is okay, let's see one that's nonlinear. Well, let's do one really easy. Let's go 2 times t times y dy dt plus ty equals 0. Well, it looks the same. Same sort of format. Why is it not linear? This is first y. Okay. You have a derivative, and then in front of it you have a function. That function is not just directly a function of t, right? It's got a y in there too. Okay, so that y prevents it from being linear. Let's get a new piece of chalk. Let me write up a few, and you can tell me some things about them. All right, let me give you one more definition. Throw on, and then we'll just a few examples. All right. So assume we have a linear. I can generalize this definition, but I don't want. Well, the first thing I want to do is shorten the notation. Okay. Another way I could write this, if I want to use this notation, is, well, I still have to keep these a and t's, okay, but then I can write this as just y to the n, where I put the parentheses around the n, so I know I'm meaning the nth derivative, okay, plus a n minus 1 t y to the n minus 1, plus a1 t y prime, or y to the 1, plus a0 t y, which you can also think of as y to the 0. The 0th derivative is just the function, equals g. Okay, so this is a little shorter way to write it, but it means the same thing. Okay? Just take the nth derivative, and minus first derivative, y to something. So I have a linear differential equation, okay, which we write it as a an. I'll even, I want the other. Plus an minus 1 of t y to the n minus 1 plus a1 of t y a0. Okay, there's my linear differential equation. Right, it's just the same thing. Copied it. We'll call it homogeneous. And like milk. If g of t, this function on the right, is 0. Okay. Otherwise, we call it non-homogeneous. What's that? Heterogeneous?
Yeah.
What's your explanation for calling it hetero instead of homo? Yes?
Diff is the same.
You see the non-homogeneous.
Oh, not that this is okay, you're not saying this should be heterogeneous and non-heterogeneous, but
Yeah.
homogeneous and heterogeneous. Yeah, sure. Okay, that's fair enough. I'm not going to do it, because I don't buck tradition. But, yeah, that's a good idea. Okay, so the reason why we have this is it's going to turn. Well, remember when we proved yesterday that if you wanted to show that every function that had an antiderivative, it had a unique antiderivative, that we first actually showed that just for 0, right? That was the part. We had a proposition and a corollary. And the proposition said, if you have a function whose derivative is 0, right, then it came from a constant function. So the reason why we make this distinction, homogeneous, non-homogeneous, is what you will often do when you want to solve a linear equation, which is non-homogeneous, is you will first solve the homogeneous version of it. Right? This is 0, and then you use that to find the non-homogeneous solutions. So that's why this becomes interesting. Okay, so let's write up an example. And then you guys can tell me how you would classify. So let's have, let me try to stick to this notation. Y squared, second derivative of y, plus 4 times first derivative of y, minus 2y equals 0. Okay, how would you classify this differential equation? It's linear, excellent, right? Because it's okay, it's got derivatives, okay, and everything in front of those derivatives are functions of t. Okay, good, it's linear. What else do we have? It's homogeneous because it's a linear, okay, it's a linear, and then it's homogeneous because it's equal to 0. Okay, that's two things, so it's linear and homogeneous. And, well, we have one other thing over here. Order, right? So second order. Okay, so this is a second order homogeneous linear differential equation. That's not bad. That's quite a mouthful. You call your parents tonight. What are you learning? Well, I learned about second order homogeneous linear differential equations. I like that. You know, they're like, okay. And that's probably a good way to make things. You just walk into a room saying that. Second order, homogeneous, linear, differential equation. I think you'll make a lot of friends that way. That's how I met my wife, actually. Let's do another one. Let's make it more complicated to start. Okay. dy dt equals minus t over y. All right, so let's try to answer some questions about it. We want to know the order, we want to know if it's linear, we want to know if it's homogeneous. What's the order? First order, right? Okay, that's easy enough, right? You just look for the derivatives. Okay, is it linear? Now it's important, when we wrote this definition of linear, we can put it in the form. And so, you know, when I write it like this, well, maybe there's some nice way of rearranging it. Okay? Let's see, let's move everything over as much as we could. So we can multiply both sides by y, and we get y dy dt equals minus t. Okay? Now, when we put it this way, it actually should be very clear. Right? We have a function of t on the right. We have our derivative, and we've multiplied it by a y, right, which is not t. Right? There's no. This is something which is not a t, so that's bad. Okay? We don't just have a straight function of t. So this is definitely not linear. About homogeneous. Well, when it's not linear, we didn't even define homogeneous. All right, so we just don't even talk about it right now. But, well, let's just think intuitively. Even if this was non-linear, you don't want this to be homogeneous, right? Because it's got a function of t over here which is not 0. Right? And that's what homogeneous meant, right? You put everything with the y's on one side and everything without the y's on the other side, right? And the thing on the other side, if it's homogeneous, should be 0. And this one doesn't have that property. It's kind of minus t over there. So, you know, we would think we shouldn't define it to be homogeneous either. But as we've defined it, we only know it for linear. And that's fine. We're only deal with those. Okay. However, there is something nice about this differential equation, even though it's not linear. Okay? There is something nice. It's called separable. And I'll show you what I mean by that. So from here, let's recall, right? I can actually think of this as dy divided by dt. And if I do that, I can multiply both sides by dt. And when I do that, I get y dy equals minus t dt. I put all the y's on one side, and I put all the t's on the other side. And when I can do this, I'm going to call the differential equation separable. I can separate out the variables. So, and we're just going to deal here with the first one. So a separable, is that ER or AR? Is it ER? I think it's AR. Separate.
It doesn't matter.
Let's take a vote. ER or AR? Who's ER?
I'm not going to vote him off.
One.
Spelling.
Who's AR? Well, I count as triple, so we're going to go with the A.
Let me see if I can check.
But you guys can make fun of me later if I'm wrong. Okay, so a separable first order differential equation is a differentiable equation. Separable is a differentiable equation. Well, of course it's first order. That can be put into the form. Well, I'm going to write it down in two different ways. Let me start with this way. So it should be a function of y times dy equals a function of t times dt. Or, if you'd rather see derivatives, f of y dy dt equals g of t. So it's linear, I mean it's first order because you have dy dt. It's probably not linear because here you have a derivative and next to a function which is not a function of t. Right, so it's probably not linear. Okay, but it's just a function of y. And then on the right you have a function of t. Okay, so this, either one of these are the same, is what we call separable. Now, so we're running short on time. Let me just tell you why it is that we care about separable first order differential equations. So let's start with f of y dy equals g of t dt. All right, so this is a separable first order differential equation. Why do I care? Well, I have a function times dy and a function times dt. I can take the integral of both sides, right? And it's perfectly well defined. I can look at this now. Okay. Now you may notice that why is he dropping the f of y, right? Just f and g here. I mean, it's the same thing. It's just I'm just being lazy. Okay. When the context is clear what they're functions of, then okay, we drop it.
By the way.
You were right. Who else? Who else? Did you vote for A? Wait, what are you trying to do? Happy you're going to fail. That's all I'm saying, right? Try to teach
English class.
Okay, so the reason why we like this is we can take, just immediately, we can take the antiderivative of both sides. Why is that helpful? Well, it gives you information, right? There's something else going on here, right? You know you have these two sets, and the base functions, right? These antiderivatives, they only differ by a constant. Okay, so I think I cooked up an example to play around with here. So, yeah, let's just start it. Really the same example. Let's do this example. So we wrote in this form, y dy equals minus t dt. We take the antiderivative of both sides. Now, we know the antiderivatives are going to be sets. Not for long. I mean, we won't think about them that way for long, but at least one more day they will be. Okay, so let's look at this first one. What's the antiderivative of y? Right? You get a function whose derivative is y.
1/2 y squared.
1/2 y squared. That works. Okay, let's see. And over here, well, again, we know I'm being really mean. I'm using the exact same constant. What's going to be an antiderivative of minus t? Negative 1/2 t squared. Plus c. Okay, so it tells us that these steps are equal. Okay, that means for everything in here, there's a corresponding function there, and vice versa. So if I take, for instance, 1/2 x squared plus 0, it has to be in this set. Right? Just drop the c, right? And you can let c be 0. 0 is a nice real number. 1/2 y squared is in this set, so it must be in this set. So this means that there exists some c such that 1/2 y squared, well, it's in this set. It should equal minus 1/2 t squared plus c. Okay, so let me see. Let me move the t's over. Okay, so 1/2 t squared plus 1/2 y squared equals c. Of course, these 1/2s are really annoying, so let me multiply everything by 2. So t squared plus y squared equals 2c. Okay. Now, c is a constant, just some c that we found. 2c, again, just a constant. So this tells me that I actually could have chosen my constant differently to suck in that 2. So this tells me there exists some real number d, which is actually just 2 times c, such that t squared plus y squared equals c. D is just 2, of course. And what this tells you is that the solutions to this differential equation, well, remember y is the function we were looking for. It's going to satisfy this equation, which, oh, what is this equation giving you? T squared plus y squared equals something. Normally you think about it as x squared plus y squared equals r squared. Circle, right? The equation of a circle, x squared plus y squared, a circle centered at 0, 0, right, with radius r. In this case, the radius is the square root of d. So those are what are going to be the solutions to this differential equation, are these all possible circles, right? Okay, so those are the solutions. In any case, this is now a nice solution. And the reason why we could do it is because it was really easy starting from a separable differential equation. Okay, enough for today. Was everybody able to find the website?
Not yet. I don't have the internet yet. So.
Oh, okay. You should find it because you need to get the homework. Go to computer lab. And if those of you who were not, yeah, so Jen and Dina and Jenna, if you could write down on just a little piece of paper for me